Welcome to this video. This is the second part of a series I'm making about building your own 3 degree of freedom robot using 3D printed parts and servo motors. In the last video, I just gave you a short introduction about this robot. The goal of this series is for you to learn robotics by doing. But even if you don't want to deal with all the hardware, I'm also providing a simulated 3D robot for you to follow along. So now let's talk about the geometry behind all of this and how can we make a certain XYZ position be reached by giving certain angles to the different motors of the robot. Alright, so let's see how the geometry of this robot works. We have here a drawing of our robot, and the goal is to find a point here at the end, XYZ. And we want to find the angles of each motor to reach that point. So maybe there's a global coordinate system here. That's Z there, X, Y, and we want to find, the point P in this global coordinate system. We're going to be having 3 motors, so each motor gets its own coordinate system. So for this first one over here, let's say it matches perfectly the global coordinate system at first, and it's going to have this θ1 angle, right? Like this is our motor. For the second motor over here, let's call it the blue motor. It's going to have the z-axis here matching the axis of the motor. Maybe this is the x-axis, that's the y. And using the right-hand rule, we have here our θ2 that we want to find. And let's call the last one the green motor. Here along the axis of that motor, that's going to be our z-coordinate. Maybe this is the x-coordinate and this is the y-coordinate. And again, right, we want to find the θ3 over here. The link lengths that we have are going to be this one over here. Let's call this L1. We have this link length over here. That's our L2. And we also have our last link here. That's going to be L3. Now let's flatten this robot into a 2D drawing to make everything easier. Right, so let's call here our first link red, the red link. It's gonna look something like this. It's gonna have L1 length. We're gonna have our blue link somewhere like this with L2 length, and our last link here, L3. The goal is to find angles θ1, θ2, and angles θ3 to reach point P here at the end, which is going to be X, Y, and Z. Now, given this simplified version, we can take the top view of this robot. So imagine somebody's looking straight down here, right? So maybe there's a eye here, and then you can see the robot from top down. Well, you can see that with the link number 1 is just going to be a point because you're looking at it right from the top, right? So let's draw what we see here. So maybe we have our link here. L1 is now just a point. And now we have our link 2 here and our link 3. We have our point P here in the end, right? X, Y, Z. That's what we want to find. And our global coordinate system is still the same. So Z is pointing out of the page right here. We have our X coordinate and our Y coordinate. And don't mistake the coordinates for the point, right? Like that's the X axis, Y axis, and Z axis. And these are the points that we want to achieve, the point X, Y, Z at the tip. Well, from this drawing, it becomes clear to us, right, that this distance over here, that's just going to be X on this side, and that's just going to be Y over here. Why is that useful? Because we can already find our angle θ1 over here. If you look from above, that's the angle θ1, right? How the link L1 is being rotated here. We can say that θ1, that's just going to be the inverse tangent, or this a tan 2 function of y and x. So that's our first equation, right? We just need the point that we want to find, and we can find theta 1 already from that. Let's just note down here another important dimension. That's going to be this projection over here, this distance from the point all the way to the origin over here. Let's call this r. That's going to be important later, but r, that's the square root of y squared plus x squared. Let's just save that for later, right? Now, how do we find our angles theta 2 and theta 3? Let's take another projection here. This time we're going to be looking right here in this direction at 90 degrees from our links 2 and 3. So again, there's an eye over here, and he's looking at our robot from that position. How can we draw this now? Well, now we can see our link 1 once again. I'm going to call this L1. Our link 2, dimension L2 is like this, and our link 3 is like this. And once again, we want to find our point P right here. Let me make this link 1 a bit bigger, just so it's easier to explain. So maybe like it goes down here. So now we have our point P over here, and we have our global axis Z pointing in the direction of L1, but X and Y, we don't really know where they are because we are looking at a projection. So we cannot say that X is in this direction, for example, because we're looking at the projection. So let's just write the Z for now. We want to find, once again, our angles theta 2 here and our angle theta 3 over here. Now, why was that dimension R important? This dimension R over here is exactly this distance over here. The distance from point P all the way to the Z-axis in the horizontal projection. And we can also find another useful dimension here. Let's call this distance over here S, right? R we already have. S is just going to be L1 minus Z, right? Z is the point that we want to achieve here at P. P, X, Y, Z, which is this position here, right? Z. Now, how can we find the angles theta 2 and theta 3? Well, let's draw another useful triangle here. This one over here. And this dimension is going to be D. And let's call this inner angle here alpha. Which equations can we get from this? Well, if we just look, I'm going to use here a purple. If we look at this triangle over here, right? That triangle, what can we figure out? That's also a right triangle, so we can say that D squared is going to be equal to S squared plus R squared, right? Just the Pythagorean theorem. Now, what other triangle can we find? What about this one here? There's a triangle right here. It's not a right triangle, but we can use the law of cosines to figure out D. And if you remember from your geometry class, we can say that D squared, it's similar to the Pythagorean theorem, but it works for triangles that are not right triangles. It's going to be equal to L2 squared plus L3 squared minus 2 times L2 times L3 times cosine of alpha. And one important thing here is that this alpha here and this theta 3, they add up to 180. So we can actually simplify this cosine of alpha here to the minus cosine of theta 3. Because they add up to 180, it's a property that the cosine of these two complementary angles, they have this relationship where the cosine of alpha is the negative cosine of theta 3. Now, these two equations have D squared on the left side, so let's set them equal to each other. So we can say that S squared plus R squared equals to L2 squared plus L3 squared plus 2L2 L3 cosine of theta 3. And then we can further simplify this to cosine theta 3. That's going to be equal to s squared plus r squared minus L2 squared minus L3 squared, all of that divided by 2L2 L3. And there you go, you found the equation for theta 3, right? Because now we can say that our theta 3 is just going to be equal to the cosine, the inverse cosine of this dimension here. Let's call this d here. So we found our theta 3. Now, all we're missing is theta 2. And how can we find that? Well, let's first define some useful angles here. Let's call this whole angle over here, let's call this phi. And this smaller angle, let's call this psi over here. Now, why are they useful? They're useful because theta 2 is just going to be equal to phi minus psi. So as long as we find those angles, we also find theta 2. Now, how can we find phi? Let's start with that one. Let me draw here in orange, maybe, this triangle over here. And you can see right away that this dimension here, S, and this dimension here is R. And phi is this angle over here. So we can say that phi is just going to be the inverse tangent, or the a tan2 function of S and R, just like that. And let me, just like that. And now to find the psi angle, let me draw here in another color. Maybe let's pick pink. We now have this. Oops, that didn't work. Let's pick pink. Yeah. We can see this triangle over here that I'm coloring in pink. Now, why is this triangle useful here? Because this dimension over here, that's L3 sine of theta 3 by looking at the smaller triangle over here, right? And this dimension over here, that's L3 cosine of theta 3. And this dimension from here to here, we have, which is L2. So we actually have a triangle that we can use to find our phi. So phi is going to be equal to the inverse tangent, or the a tan2 function of what's the smaller side of a triangle, L3 sine theta 3. So L3 sine of theta 3. And what's the bigger side? That's L2 plus L3 cosine of theta 3. So L2 plus L3 cosine of theta 3. And there you go. You have these two equations that you can plug in here, and then you find your theta 2. So now you have all the three equations for the three angles, the theta 1, theta 2, and theta 3, and they're all functions of either your point xyz and the link lengths. But that is all that I have for this video. In the next part, we'll be talking about putting this robot together and connecting all the electronic components. Thanks for watching, and I'll see you in the next video.